In this video, we'll begin our section on propositional logic. So first, the definition of a proposition. A proposition is a sentence to which one and only one of the terms, true or false, can be meaningfully applied. So for example, a sentence like 4 is even, or even something like 4 belongs to the set 1, 3, 5, or 43 is greater than 21. These are all propositions. And then we'll use logical operations. So in terms of English words and phrases, these are phrases like and, or, not, if and only if, then. And these can be added to one or more propositions to create a new compound proposition. So along with propositions and compound propositions, one convenient way of determining truth values will be to use what is called a truth table, and we'll see our first example here. So the first operation we'll introduce is logical conjunction, and this corresponds to the English word and we'll denote it using this symbol that looks like an upside down V. So if you see this string, P upside down V Q, you read that as P and Q. So the truth table is below, and the way that we think about the truth table is this is all of the possible combinations of truth values. So the first column is for P. So given a proposition P, it can either be true or false. Given a proposition Q, it can also either be true or false. So then together we get these combinations. We can either have P is false, Q is false, or P is false, Q is true, or P is true, Q is false, or P is true and Q is true. So notice here that for true, we're using the number 1, and for false, we're using the number 0. But in our course, we'll also be using the capital letter T and the capital letter S. So you'll see truth tables written in this form, either with 0s and 1s, or capital T's and capital F's. And then the third column, P and Q, is telling you the outcome depending on the values for P and Q respectively. So if P and Q are both false, then the conjunction P and Q is also false. If P is false but Q is true, the conjunction is still false. If P is true but Q is false, the conjunction is still false. The only way for the conjunction to be true is for both P and Q to be true. So this is the particular truth table for conjunctions. Because we're using the English word and, the way we can think about it is that only one of the statements being true is not enough. We need both statements to be true in order to say that the conjunction P and Q is true. All right. We also want to point out that we'll generally use the lowercase letters P, Q, and R for propositions. This is the most common thing, just like we most commonly use X, Y, and Z for variables. All right, so the next operation we'll introduce is disjunction, and this corresponds to the English word or, and we'll denote with the symbol flipped upside down. So now it looks like a V. And you'll read this P or Q. So it has its own truth table. Again, the first two columns are just showing you the possible combinations. P is false, Q is false, or P is false, Q is true, and so on. And then we'll see that the third column gives us the truth values for P or Q under these situations. So in order for P or Q to be true, we only need one of P or Q to be true. So you can see here, if P is false but Q is true, we're true. If P is true but Q is false, P or Q is true. And if they're both true, then P or Q is still true. So the only way for it to be false is for them both to be false, because we only require one of them to be true in order for the disjunction P or Q to be true. Then we'll discuss the negation. So negation is acting only on a single proposition. So you just have a single proposition, say P. Its negation corresponds to the English word not, and we'll denote it with this symbol. So the truth table here is a bit smaller because we're only talking about what if P is false, then not P or negation P is true, whereas if P were true, then not P or negation P is false. So that's pretty straightforward. Now, the next thing we want to introduce is what is called a conditional statement. The conditional statement, if P then Q, will denote with this arrow. Or you may sometimes hear me say P implies Q. So these are the same notion. If P then Q. And some examples of this type of compound statement are, I'm going to quit if I don't get a raise. We could write this as, if I don't get a raise, then I'm going to quit. So sometimes these statements aren't exactly in the form if then, because with the English language, we have many different ways of saying the same thing. But the sentence can be rephrased in this form. If I don't get a raise, then I'm going to quit. Or, for example, if I pass the final, then I'll graduate. I'll be going to the movies, provided that my car starts. So we again have a truth table for this situation, and because we're working again with two propositions, P and Q, we have these 4 rows denoting the 4 different combinations, either false, 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 true, true, false, or true, true. And then you can see in the table the result. The conclusion is, well, if the hypothesis P is false, then it doesn't matter about Q. The total statement will be true. And if the hypothesis P is true, and that leads to the conclusion Q also being true, then the compound statement P implies Q is true. So the only way for the implication P implies Q to be false is if you start with a true hypothesis, but your conclusion Q is false. So another way of saying that is here, a conditional statement is meant to be interpreted as a guarantee. If the condition is true, then the conclusion is expected to be true. It says no more or no less. So let's walk through a nice example that I think will make this a little bit clear. So assume your instructor has told you if you receive a grade of 95 or better in the final, we're going to call that P, then you will receive an A in the course. We'll call that Q. So it's an if-then statement. We can think of it as P implies Q. And we'll consider the 4 different cases. Suppose your final exam score was less than 95. Then P is false, and you did not receive an A. Then Q is false. We say that your instructor told the truth. You didn't meet the criterion for which he promised you an A, and you didn't get an A, so that's fair. Case 2. What if your final exam score was less than 95, so P is false, but you did receive an A in the course, so Q is true? Well, we still say that the instructor told the truth because perhaps your overall average in the course was good enough for you to still get that A. He never said that the only way to get an A was to get a 95 on the final. He just said if you get a 95 on the final, then you will get an A. So the first case was false implies false is true. The second case, false implies true, that's also true. Now let's see the third case. What if you did receive 95 or better on your final, but your instructor didn't give you an A? So P is true, but Q is false. Then you're going to feel like your instructor lied. He didn't fulfill his promise. So that's true implies false is false. And then finally, if you received a score greater than 95, so P is true, and your instructor gives you the A, so he fulfilled his promise, then again we say he told the truth, so this is true implies true is true. So you can see from this example why, for a conditional statement, the only way for the statement to be false is if the hypothesis is met or the condition is met, but the result doesn't follow. It's important to note that if we switch the places of P and Q, which are called the condition and the conclusion respectively, if we switch them and instead we have Q implies P, this is in general not the same. So this is what will be called the converse of a proposition. Our statement was if P then Q, then the converse would be if Q then P. So for the example of the grades, the converse would be if you receive an A in this course, then you received a grade of 95 or better on the final. It should be clear that these are not the same idea. So in general, we don't want to make the mistake of thinking that we can interchange P and Q, and that's why the arrow goes in one direction. But there is a proposition relating to P implies Q, which does have the same logical meaning. That's called the contrapositive. The contrapositive of the proposition P implies Q is the proposition not Q implies not P, or if not Q, then not P. We'll see that this will have the same logical values as the original proposition P implies Q. So there are going to be some cases in this class and in the future where it's going to be easier to work with not Q implies not P than to try to directly show something from P implies Q. So the contrapositive is a powerful tool that we could use in the future if we're trying to understand something about the statement P implies Q. Now, one other thing we want to introduce is what is called a biconditional statement. If P and Q are propositions, the biconditional statement in simple English is P if and only if Q. And we denote that using the double arrow. And the truth table is seen here. So P if and only if Q will be true if we have P false and Q false, or if we have P true and Q true. So P if and only if Q is only true when both of the truth values are the same. Whether they're true or false doesn't matter. If they're the same, then it's true. If they differ, then it's false. And in writing, you will often see this abbreviated. Instead of writing these words, if and only if, you'll see this abbreviation IFF. So if in the future you see the abbreviation IFF, you know that what we're talking about is P if and only if Q, or this biconditional with the double arrows. Again, because the English language is very flexible, we have several different ways to describe these, and you'll see them all used interchangeably. So you want to make sure that you understand that these are all equivalent to the statement if P then Q. So the conditional P implies Q, can be if P then Q, or it can be P implies Q. These are probably the most common, but you'll also see this should say Q follows from P. That means the same thing. Or you'll see P only if Q, Q if P, P is sufficient for Q, Q is necessary for P. So all of these are the same as P implies Q. And then the biconditional, P if and only if Q, is equivalent to saying P is necessary and sufficient for Q, or P is equivalent to Q. Also, if P then Q and if Q then P, if P then Q, and conversely. So any of these ways of stating it, we would understand that that just means the biconditional P if and only if Q. Now we're ready to work through some examples together. So the first exercise says, let D be the proposition, I like discrete structures, C be the proposition, I will pass this course, and S be the proposition, I will do my assignments. Then we're given sentences, and we're asked to express each of the following in the symbolic form. So the first sentence is, I like discrete structures, and I will pass this course. So we know that I like discrete structures is D. Then we see this conjunction and, so we use the upside down V symbol, and I will pass this course as C, so this is D and C. What about I will do my assignments or I will not pass this course? Well, I will do my assignments as S. I will pass this course as C. That means that I will not pass this course should be negation of C. And we have the disjunction or, so we use the symbol that looks like a V. Then it is not true that I like discrete structures. That should be negation D or not D. And I will do my assignments. So I use and, S is I will do my assignments. Then I will not do my assignment and I will not pass this course. I will not do my assignments should be negation S. And I will not pass this course is negation C. So this is how we would express them in symbols. First, we have to assign a letter to each proposition, and then we use our negation, conjunction, and disjunction. Our next exercise says for each of the following propositions, identify simple propositions, express the compound proposition in symbolic form, and determine whether it is true or false. So for A, the statement is the world is flat or 0 is an even integer. So let's assign them names. Let's say the proposition P should be the world is flat. And the proposition Q should be 0 is an even integer. Then symbolically, we can represent this statement, the world is flat or 0 is an even integer, as P disjunction Q. And then we want to determine if that's true or false. Well, I only need one of them to be true because it's a disjunction and we know the truth table. So we have the world is flat, that's false, or 0 is an even integer, that's true, so the total statement is true. False or true is true. Now for B, we have if 432,802 is a multiple of 4, then 432,802 is even. So let's let P be 432, 802 is a multiple of 4. Let's let Q be, it is even. Then our compound statement, since it's an if-then statement, is P implies Q. Now, 432,802 is not a multiple of 4, so this is false, implies true. It is even, and that's true. The hypothesis of a conditional statement is false, then the total statement is automatically true. It doesn't matter about the conclusion. Now we have 5 is a prime number and Q is not divisible by, and 6 is not divisible by 4. So one proposition will let it be 5 is a prime number. And then one proposition will let it be 6 is not divisible by 4. Then we have, this is and, so we have conjunction P and Q. And we know that 5 is a prime number, so this is true and true. True and true is true. For D, we have 3 belongs to Z, 3 belongs to the set of integers, 3 belongs to the set of rational numbers. This is also conjunction, so we have P and Q. And 3 is an integer, it's also rational. True and true is true. But what about if we have 2/3 is an integer and 2/3 is rational? Again, conjunction, so P and Q. And I know that 2/3 is rational, but it's not an integer. So this is false and true. False and true is false because we need them both to be true for conjunction. Finally, the sum of 2 integers is even, and the sum of 2 integers is odd. Rather, the sum of 2 even integers is even, and the sum of 2 odd integers is odd. Let's put that in here. Even, odd, and we have a conjunction, and. Well, the sum of 2 even integers is certainly even, but the sum of 2 odd integers is not odd, so this is true and false. Again, false. All right, then the next exercise is let P equals, or let P be the proposition 2 is less than or equal to 5, Q be the proposition 8 is an even integer, and R be the proposition 11 is a prime number. Express each of the following as a statement in English and determine whether the statement is true or false. So going in the other direction now, we have the statements in logical symbols, and we want to determine if they're true or false. So for part A, since P is 2 is less than or equal to 5, not P should be 2 is strictly greater than 5. So this will become the statement 2 is greater than 5, or 8 is an even integer. And again, because we have the disjunction or, we only need one of them to be true. So the fact that 8 is an even integer is enough to say this is a true statement. Then the next is if P then Q, or P implies Q. So if 2 is less than or equal to 5, then 8 is an even integer. Also true, because we have a true statement, 2 is less than or equal to 5, implying a true statement. So true implies true is true. So here I want to say this was false, or true is true. This is true implies true is true. Okay. Next, P and Q implies R. So P and Q would be 2 is less than or equal to 5 and 8 is an even integer. This is an if-then statement, so let's say if 2 is less than or equal to 5 and 8 is an even integer, then (11) is a prime number. So what we have is 2 is less than or equal to 5, that's true, and 8 is an even integer, that's true, implying 11 is a prime number, that's true. So in all, this is a true statement because it becomes true implies true. What about P implies Q or negation R? So negation R then should be 11 is not a prime number. So this should be if 2 is less than or equal to 5, then 8 is an even integer, or 11 is not a prime, so we have true implies true or false, which is true implies true. So that's true. P implies negation Q or negation R would be if 2 is less than or equal to 5, then 8 is not an even integer, or 11 is not a prime. So we have a true hypothesis, 2 is less than or equal to 5, implying 8 is not an even integer is false. We have disjunction, 11 is not a prime is false, so this becomes true implies false, and that's false. The last one we have is negation Q implies negation P. So that will be if 8 is not an even integer, then 2 is greater than 5. 8 is not an even integer is false. 2 is greater than 5 is false. So we have false implies false, which is true. Okay. Next, we want to rewrite each of the following statements using other conditional forms. So we have statements like, if an integer is a multiple of 4, then it's even, or the fact that a polygon is a square is sufficient for it is a rectangle. So I'll go back and remind us that we said that all of these conditionals are the same. P implies Q, Q follows from P, P only if Q, and so on. So this is what the question is asking us to do. We get to choose which one we want to change it by, but we're just going to change it into another equivalent statement. So how about an integer is a multiple of 4 implies that it is even. So these are exactly the same statement. Instead of the fact that a polygon is a square is sufficient that it is a rectangle, we could say the fact that a polygon is a rectangle is a necessary condition for the fact that it is a square. For C, the statement is if x equals 5, then x squared equals 25. So we could say x squared equals 25 if x equals 5. Instead of if x squared minus 5x plus 6 equals 0, then x equals 2 or x equals 3, we could say x squared minus 5x plus 6 equals 0 only if x equals 2 or x equals 3. Or x squared equals y squared is a necessary condition for x equals y. We could change that by x squared equals y squared follows from x equals y. So these are all of the different ways that we can change these statements, and these will all be equivalent to their original if-then forms. Now we're asked to write the converse of the propositions in exercise 4 and compare with the truth of each proposition. So we weren't asked to check the truth of the propositions in 4, but I believe that these were true. An integer being a multiple of 4 implies that it is even. It's true. The fact that a polygon is a rectangle is a necessary condition for the fact that it's a square. It's true. So all of these are true. Now it says change them by the converse, and let's see if they're still true. We know that the converse is not, generally speaking, logically equivalent, so there's a good chance they might not be. So instead of an integer is a multiple of 4 implies that it's even, we can say if an integer is even, then it is a multiple of 4. So I switched the roles of the statements. If I said that P was an integer as a multiple of 4 and Q was an integer as even, before I had P implies Q, now I'm doing Q implies P, and you can see that this is false. There are plenty of even integers which are not multiples of 4, like 2. Okay, instead of saying the fact that a polygon is a square is a sufficient condition that it is a rectangle, we could say if a polygon is a rectangle, then it is a square. So again, I've switched the roles. In question 4, the statement was equivalent to if a polygon is a square, then it is a rectangle, which we know is a true statement. A square is a special type of rectangle. Now our statement is if a polygon is a rectangle, then it is a square. That's false because a square is one special type of rectangle, but it's not representative of all rectangles. In question 4, we had if x equals 5, then x squared equals 25. So the converse would be if x squared equals 25, then x equals 5. We also know that that's now false. These are not interchangeable because we know that for x equal to -5, we would also have x squared equals 25. And we had if x squared minus 5x plus 6 equals 0, then x equals 2 or x equals 3. So we can change that to if x equals 2 or x equals 3, then x squared minus 5x plus 6 equals 0. Now let's think about this one. Is this true? This is still true. So it was true when we said if x squared minus 5x plus 6 equals 0, then x equals 2 or x equals 3. And it's true going the other way. That means that this is actually a biconditional statement. We could have written this as an if and only if statement to start with. So there are instances when the converse will hold, but it's not usual. Okay, finally, we had x squared equals y squared is a necessary condition for x equals y. Or equivalently, x squared equals y squared follows from x equals y. So that's basically if x equals y, then x squared equals y squared. Our converse should be if x squared equals y squared, then x equals y. And again, this is false. Think again about the x squared equals 25. You can have 5 squared equal to -5 squared, and that doesn't mean that 5 is equal to -5. So this exercise illustrates that the converse is most of the time not going to be equivalent, and we want to make sure that we don't make that mistake. There's a little bit more about truth tables in this lecture note, and it's just expanding the idea a little bit to say when we're working with 3 propositions like P, Q, and R, as we saw in our example exercises, this table continues to grow. Because remember, the first 3 columns are going to be all of the possible combinations for true and false between these 3. So we have now false, 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 true, false, true, false, false, true, 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 false, false, true, false, true, 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 false, true, true, true. So these are all different situations. Now there are 8. So if we think about our truth table for negation P, it had 2 rows because there were 2 possibilities, true or false. Then the truth tables for our disjunction and our conjunction had 4 rows because when we introduced 2 statements, we had 4 combinations. So now with 3 propositions, we have 8 different combinations. And so it's going to be true that as we keep growing, the truth table will have 2 to the power n many rows, where n is the number of propositions. So this is just a nice example of compound propositions including 3 propositions and what a truth table might look like. And in this class, we're going to make sure that we're able to construct such a truth table. The way that you do it is just going line by line. You think of it as the smaller pieces. Eventually, we want to get to something big like P and Q, or negation Q and R. So we have to first find P and Q. Then we have to find negation Q. Then negation Q and R. Then when we put them all together, the final column here is this column or this column. So we know that since it's disjunction or, we only need one of the truth values to be true, and you'll see that that's exactly what's happening. If one of the truth values in these 2 columns is true, then we get true. Otherwise, if they're both false, then we get false.